all about removal of low concentrated phosphorus from aqueous solution by waste seashell aragonite crystals. And here I'm gonna deal with very low concentration of phosphorus, which experimentally means phosphorus was 1 milligram per liter. And the table of content includes the synthesis of nanoaragonite and then the treatment of phosphorus. Through response surface methodology was used to statistically analyze the experimental parameters. And the sustainable development goals. We all know that during Paris Agreement, 17 sustainable development goals have been set. And among those 17 development goals, my work deals with goal number 6, which is clean water and sanitation, and goal number 13, climate change. And what is eutrophication, or why eutrophic water is a problem? So eutrophication occurs when water body becomes overly enriched with nutrients. Overly enriched with nutrients means enriched with nitrogen and phosphorus. These nutrients are, you can consider these nutrients as a food for algal blooms, and once these algal blooms develop and when they die, they consume a huge amount of dissolved oxygen, and that's why there is a shortage of oxygen in the water for other aquatic animals, and that's why the aquatic ecosystem being start degrading. So the removal of phosphorus particularly is very critical. And now this is the present status on the world, and you can see the dark red brown shade, which signifies the water, underground water or surface water contaminated with the phosphorus. Generally, phosphorus in surface water, for example, lakes, ponds, they are contaminated with 1 to 2 milligram per liter of phosphorus, which is enough to cause serious eutrophication. That's why in this experiment, we prefer 1 milligram per liter of phosphorus to be treated with aragonite. Now, another question is why we choose seashells. Actually, seashells are composed of calcium carbonate, and it's better not to consider them as a waste, but to consider them as a resource. But in these days, these wastes are being dumped in the landfills or open spaces, and in the open spaces, they can emit hydrogen sulfide or ammonia and other amine gases. And other applications, for example, some of the applications of seashells, maybe you can see in some tourist places, they can use as handicrafts, like showpieces, and other used as fertilizers or some part in cement as well. So more applications are required for these seashells, and the quantity in which they are dumped in the landfill is too high. For example, in China is greater than 10 million tons, and others like Thailand, South Korea, they are among other countries which are dumping seashells in the landfills. Now, the aim and objective of this study is to synthesize the value-added product from waste seashell in the form of aragonite. Second, utilization of these synthesized aragonite for the removal of low concentration of phosphorus from the wastewater or aqueous solution. Now, coming to the synthesis of aragonite is quite simple but complex. Why? Simple part is, okay, seashells are dried, grinded, calcinated at 900 degrees Celsius. Okay, very good. But the critical part is how to make aragonite. Because if the process is not being controlled, aragonite will not be synthesized. In fact, calcite will be formed. So to control this nucleation process, we added magnesium chloride, and the magnesium to calcium ratio is also critical, which we will discuss later. So here magnesium chloride is added, and then the carbon dioxide chloride is being controlled very carefully. So 50 centimeter cube per minute carbon dioxide was introduced, and then when the pH, because once you introduce carbon dioxide, the pH starts decreasing, and once pH reaches constancy, then we consider the reaction to be finished, and then only the aragonites are synthesized. Another critical factor here is the temperature, because Temperature around 80 degree favors the nucleation and the synthesis of aragonite rather than calcite. Now, as I mentioned before, this is raw limestone and these are other seashells. You can see the composition of limestone is very much similar, not exactly same, but very much similar to the seashells. And now the XRD and so here I put extra eggshell, okay, chicken eggshell. Why? Chicken eggshell is mainly calcite, but in other seashells, they include mineralogical phases, calcite and aragonite, both included in different proportions. That's why, just for the comparison, eggshell was introduced to show that eggshell is only calcite, but the other seashells are having both in different proportions, aragonite and calcite. Now, once we synthesize aragonite, it's mostly aragonite. The synthesized product was mostly aragonite. Of course, there will be a small part of calcite as an impurity. And as I mentioned before, the factor magnesium to calcium ratio is very critical, and we find out that 1.8 magnesium to calcium ratio was found optimum for the synthesis of aragonite. And this was further justified by the SEM images in which we can find a good aspect ratio here. One thing is critical when magnesium to calcium ratio is very less. Here you can see there are some small, very small particles. These particles are nanocalcite. This is what we don't want. That's why we increase the magnesium to calcium ratio to obtain a pure aragonite form without any nanocalcite. And finally, the magnesium to calcium ratio which was assigned 1.8, was find optimum for the best aspect ratio also. What is aspect ratio? The ratio between the length of the particle and the diameter of the particle. That's called aspect ratio. The more the aspect ratio, the better aragonite will be. And the zeta potential, which shows the surface charge, it's all negative charge surface. So, and below 6 pH, it starts dissolving. So after 6, it's all negative charge on the surface. Now, a very brief qualitative mechanism I want to discuss is that once, like magnesium don't take part in the chemical reaction. However, it acts as a poison. That's why some people also refer it as a poison effect, because magnesium try to compress and try to take part in the nucleation of calcite and alter the formation and convert it into aragonite. For example, if we are not using magnesium, we can use other positive ions, for example, some heavy metals or something. They will also have a similar effect, not exactly same, but similar kind of effect. So here, magnesium is not actually taking part in the chemical reaction, but only influencing the nucleation of the aragonite. And then the treatment of phosphorus. So we took 150 ml of water, which is 1 milligram per liter of phosphorus concentration. And after the treatment, the results were analyzed, statistically analyzed with response surface methodology to find out the best possible parameters to find maximum removal efficiency. And then the absorption capacity in the starting is not good. It's around 1 because the concentration of phosphorus is very less. Means if we are taking high concentration of phosphorus in the solution, maybe absorption is better. But in 1 milligram per liter case, absorption is around 1.08 capacity. Absorption capacity is around 1.08. Now, we want to improve the efficiency, and for that, we check these parameters as my dosage, pH, and temperature from 60 to 140 milligram. pH, these are initial pH, because once we added aragonite, pH will rise. So these are the initial pH 3 to 7, and then temperature 25 to 45. And after doing some statistical analysis, we find out this equation, and this equation perfectly matched the experimental results with the R square value of almost 0.996, and the results come out to be, so it was observed that efficiency increases as the calcium, as the aragonite dosage increases. Second, the solubility of aragonite and absorption of phosphorus significantly depends on temperature. Means the solubility of aragonite is exothermic and the absorption of phosphorus is endothermic. Means the property of dissolving of aragonite and return reaction between calcium and phosphorus is totally opposite. That's why an uh, temperature, optimum temperature was found suitable. And then for the pH, like pH around 6, which at equilibrium is around 10, was found optimum for the maximum efficiency. And from here you can see the aragonite dosage is 140 milligram, pH around 6. This is again initial pH, and temperature around 45 was found to have 97.67% of efficiency. Now we can see in the SEM images, the phosphorus adsorption was in discrete form, not in continuous manner, but in discrete form. So my team tried to propose some mechanism here, and we find out that this adsorption process is because of the dissolved calcium. That's why in the earlier case, I mentioned about the solubility of aragonite. Okay? Well, I will discuss it in the next slide. But first of all, about the kinetics. This adsorption process follows second order reaction, and it follows Langmuir acetone and Freundlich acetone both. Langmuir and Freundlich means the adsorption will be on surface, that is confirmed by Langmuir, and Freundlich means adsorption can overlap. Means once the phosphorus is adsorbed, more phosphorus can be adsorbed over it. So that's the Freundlich acetone. And then one thing which is critical here is separation factor. Maybe not many people know about this separation factor. When separation factor is less than 1, or when separation factor follows this kind of degradation or reduced trend, it means that adsorption capacity will increase if the concentration of phosphorus or any other contaminant in the water increases. For example, here you can see when the phosphorus was 1 milligram, the adsorption capacity was 1.08. But once the phosphorus concentration was 10, the adsorption capacity increases. So that's the property of the material and the property of the overall chemical reaction. And now the effect of other ions. So I checked the sulfate is the only one which is considerably competing the phosphorus, and hence these are the phosphorus efficiency. And in the presence of sulfate, the phosphorus efficiency reduced by almost 15-20%. So yeah, in the solution, the sulfate and phosphate, of course, they will compete with each other for the adsorption process. Like lastly, I would like to briefly talk about the mechanics. I talk about aragonite solubility. There is a very small amount of calcium ions which will dissolve in the water, and because the surface charge is negative, they got adsorbed on the surface, right? And the phosphorus which was present in the water then can react with the adsorbed calcium. That's why in the SEM images, the adsorption was in discrete form. So this overall work was published recently in Journal of Environmental Management as well. And this kind of hypothesis was further confirmed by molecular dynamics, in which I thermodynamically and energy-wise, I tried to prove that my hypothesis is possible, and the distance between calcium ion and the overall aragonite shows that these are stable. And for example, with these total energies, which are under normal range, because once they are negative, it means they are more stable. Once they are in positive, they are less stable. we know that, as I already mentioned, calcium ions are absorbed on the surface. So means, of course, they will not be very stable. Almost, we can say that they can be dissolved as well. And then finally, I try to show that those absorbed calcium can further interact with the phosphorus. Finally, I would like to conclude my presentation. And in here, aragonite crystals can be efficiently and in a high purity can be synthesized with seashell, and those uh, aragonite crystals can be used for the removal of phosphorus through adsorption process. And the optimum parameters for uh, aragonite dosage 140 is, and pH 6, and temperature around 45 to achieve around 97% of efficiency. And finally, a novel mechanism was proposed illustrating the bridge in the form of calcium ions, which is responsible for absorption of phosphorus on nanolevel. Some references. Thank you for your patience.
네, 수고하셨습니다. 혹시 질문 있으신 분?
You use seashell to produce aragonite or renewable phosphorus. So among all of those seashell, which one provides the best, like considered as the best source for aragonite production?
Doesn't matter. Any seashell is okay, because as I mentioned, these seashells, they have similar composition. And once I prepare aragonite from these seashells, all aragonite have similar properties. So any seashell is good.
You described the calcium ion specifically absorbed onto the aragonite surface. Why?
Because in my experiment, we doesn't have any other positive ions, right? Because we prepare artificial phosphate solution. So in that case, the calcium ions, because there are some calcium ions which will dissolve in the water. Of course, because aragonite is not insoluble. Very small amount of calcium ions will dissolve. And because of that, the surface charge is negative. So there is a tendency for these calcium ions to absorb on the calcium surface. And because they are calcium ions, they can almost instantaneously react with the phosphorus available in solution.
Okay, so I think that you suggest the zeta potential data. So, figure 11.
Figure 11.
Okay, the line. So in the presence of the calcium ions, the positively charged surface is changed by the calcium ions.
Yes, yes, yes.
Okay, so I think that you prove this data in the presence of the calcium ions.
Okay, like in the presence of calcium ions for the surface charge.
So, good morning, ladies and gentlemen. Today I would like to present the topic, the innovative, the carbon mineralized methods for acid microbials treatment. Moving toward a circular economy, so let me move on to the content. So introduction, I will talk the reason why we study this topic. And we will also review some case studies. And at the first part, I will show you some our experience result, and finally we work some conclusion, and let me move on to introduction. So when we talk about the AMD, is now is being the challenge and opportunity. So we can see in this slide, reading the source of the AMD is can from the underground, it's scanned from the tailing. So when we want to find solution for the AMD, we need to understand where is the AMD from. So in this slide, we can see one of the example of the AMD from the one underground mine, and the feature we can see is have a many the heavy metal. So beyond the standard, the WSO and some countries, the standard is above the standard. So this means we need to find some solution to just with AMD before to release to environment. So this is the effect of the AMD. So we can see it the effect to physical, the chemical, biological, ecological, and social economical. So when we understand the effect of the AMD, we know the problem with the AMD, and we have to find solution for this. And when we can solve the problem, this means the opportunity to moving a circular economy. So it is how we can treat with the AMD. The first, we need to understand where the source of AMD and then how is the chemical component of the AMD. And we have a sequence step of framework to treat with the AMD. So this means to treat with AMD, we need to follow this step. And recently we heard many about the circular economy. So in the past, the final destination of the linear economy is the waste. But now we need to change the concept to circular economy. This means the AMD now is not being the waste. Now AMD water is like the resources. This means we can find the solution for the treatment with the AMD, and we can make profits from it to contribute to circular economy. So let me move on to more detail of some case study. So in this case study, you can see they apply the carbon sequence technology to treat with the AMD, and after applying the methods, the AMD can be released to the environment to adopt the standard. And another study from the Africa, they can treat with AMD by many site lye and soda and CO floating. And after treatment, the AMD can be used to like the drinking water, the enough adapt standard for drinking water. And for this study, they applied another method to treat with AMD, and one very interesting for this paper. After they apply the methods, the percent of removal is almost the 100%. And when they invest the $66 for treating 3.5 kiloliter of AMD, and they can collect the variable, the heavy metal. And when they sell this metal, it's like the $933. So this means now the AMD is not the waste, it's being the resources to make to contribute for the circular economy. So let me move on to our experiment result. To design our study, we make the survey for the AMD in many underground mines. So you can see this slide from the Korea underground mine, and some mine in China and some mine in Vietnam. So the most of the future we can see for the AMD is contain the heavy metal. So this means if we can apply some method to remove the heavy metal, this means we can treat with the AMD. So the key they already done with the study about how to use the carbon mineralization to treat with to remove the heavy metal. So in this study, we apply the same process to remove the hardness in the water by carbonation process. So let me move on to more detail. So you can see the carbonation for heavy metals stabilization. So after we apply the carbonation process, the heavy metal in the harness water can remove. So we apply with the four kind of the sample, the tap water, drinking water, and the water, the kilogram driver and artificial water. And this is the result for study with the artificial water. So after the carbonation, the artificial water sample harness, the removal percent is about 50 to 80%. And similar for the drinking water, we got a similar result. And for the natural water, we got the same the result. And finally, the harness removal efficiency is around 70 to 80% for artificial water, 60 to 70% for drinking water, and 70 to 85% for natural water. So we can conclude that using the carbonation process, the heavy metal could be the precipitated and the pH could be degree. So this means we can conclude that we can apply the carbonation method to treat with the IND because the process is similar. But in this study, we just apply for the Ca and Mg iron. And how about the possibility for the IMD treatment by using the carbon mirror technology? So when we review the IMD chemical component in sulfur, we can see it's the content, the heavy metal. And for our study, we also indicate we can apply the carbon mineralization technology, can stabilize the heavy metal in the IMD. So we need the carbon mineralization process for the IMD treatment. And this is my conclusion. To make conclusion, I want to show you the video I make for this. So please turn on the. No? Okay, maybe it has some problem. It's okay. I will just so for the conclusion, now in time we need to think the AMD is not the waste. The AMD now is being the resources to achieve the circular economy, and beyond on the water paper, they can make the profits from the $66 invest and create almost $1,000 by treatment by AMD. So our experiment results are mainly indicate the carbonation process is effectively reduce the water harness in all the different harsh water sample, and also it's cost effective and eco-friendly process to compare down the other conventional methods. And there are several the conventional methods are available for removing the heavy metal in AMD, but among the simple carbonation process methods have a higher removal efficiency, and this carbonation process is economy and eco-friendly and less energy consuming compared with another conventional methods. So for the further study, we will try to apply the carbonation process for the real AMD sample. So this is everything about my study. Thank you for listening.
I have one comment and one question. Comment is you mentioned all positive points of carbonation and AMD treatment. That's really nice. But are there any limitations, like any challenge, any limitation of AMD treatment through carbonation?
Yeah. So I think the most limitation now, we already know the carbonation is a very good technology, all right? But for AMD, we need to develop like the industrial scale. We need to think how we can build the industrial scale. We not just the experiment in the lab. So I think the big problem with how we can apply the carbonation process for the AMD treatment we need to think about how we can develop in the industrial scale. This is a big problem because it needs the huge money to invest. But in the first step study, we just indicate this method is suitable to apply for the AMD. And in the second step, if they want to apply this for industrial scale, they need to have a detailed study and evaluate more detail about the economy efficient and something. Okay, thank you.
네, 다음으로 송영주 알겠습니다.
Hi everyone. Thank you for attending my presentation. And today's topic is how carbon dioxide can be utilized for removal of arsenic in wastewater. So the title is efficient removal of arsenic from wastewater by calcium oxide with integration of carbonation. The contents include the introduction and methods and resultant discussion and conclusion. Especially in resultant discussion part, I want to explain the previous study in Kiba in my lab and explain the thermodynamic simulation and molecular dynamic simulation that our team have done. This study's goal is to explain among the sustainable development goals. Number 6, clean water and sanitation. Number 13, climate action. Based on this goal from the sustainable development goals, and let's start talking about the arsenic contamination effects. So, as you can see this slide, arsenic is considered as a hazardous element in water, even in very low concentration. For example, World Health Organization, as known as the WHO, set the arsenic standard for drinking water at only 10 ppb. Among the industrial areas, the discharge of arsenic toward the wastewater set on 100 ppb. So it means removal of arsenic is very essential among the industrial areas. And the combination. Carbon dioxide from the atmosphere is thought to be crucial for global warming and climate crisis. So let's see the figure number 5. This is the predicted distribution of the temperature change due to global warming. So maybe around the average change of the temperature is around the 3. It means we need there is urgent requirement for transition toward carbon neutral society for better future. There's 2 kinds of the problems I mentioned, and I tried to solve these 2 kinds of problems simultaneously. But current state has some limitation like this. A number of the study about the removal arsenic, especially the chemical precipitation, such as line softening, is very common and very effective technology. But line softening has been documented to achieve over 95% of this removal of arsenic. It's very high efficiency, but this one has some limitation, like long-term stability of precipitation is a concern. So it means otherwise calcium arsenate is forming during chemical reaction between calcium ions and arsenic ions. While calcium arsenate is very unstable, on the rich carbon dioxide environment, atmosphere. So it means a calcium arsenate compound decompose slowly in contact with the industrial calcium carbon dioxide to form calcium carbonate, subsequently leading to strong arsenic release into the liquid phase. So this study's aim and objective is optimization of the experimental parameters for maximum arsenic removal efficiency, and second one, integration of accelerated carbonation in arsenic contaminated water to overcome the limitation of the conventional calcium-based treatment. And this is the whole procedure of my experiment. And before started the experiment, the source of the calcium oxide obtained by solutions, calcinated solution. And the calcinated solution become of calcium oxide, and calcium oxide is put into the 50 milligram per liter arsenic solution. And there's the two steps in my experiment. First step is the chemical reaction, calcium and arsenic, and second one is carbonation. First one, a chemical reaction. When it comes to the chemical reaction, just the calcium oxide mixed with the water, but not the water, the arsenic solution. And it, as a result, calcium arsenate precipitated. And carbonation, the CO2 gas injected into that solution, and the calcium carbonate would be precipitate. Actually, we can get some questions like CO2 emitting is the problem. So it's not the like the carbon neutral technology, but theoretically, in the same dosage of the calcium oxide, the both amount of CO2 emission by calcinated and the required amount to form calcium carbonate is the same theoretically, but actually experimentally not proved yet. So it will be proved later, and I'm trying that. This is the previous arsenic experiment result in Kiban. The efficiency of the result reached over the 85%, but this experiment has some limitation. First one is the result I mentioned that over the 85% can be enhanced. And this experiment conducted under the high pressure. So it means the experiment needs energy intensive to compress the CO2. And calcium dosage was 50 grams, is considerably high. And actually, when it comes to the experiment of removal arsenic, that more detailed experiments are required. So we did, before starting the experiment, we did thermodynamic simulation. There are various kinds of the arsenic ions according to pH. So it means all kinds of the arsenic removal is very challenging and very difficult. So based on this knowledge, we did the thermodynamic simulation. And let's see the figure A. This is the without carbonation. So we can see the calcium arsenate formed, and according to calcium arsenate formed, we arsenic removed. And let's see the figure C. Figure C. This is the with carbonation. The CO2 gas injected into the water or some arsenic solution, and calcium carbonate formed. But the types of the calcium carbonate forms will be, one is the calcite, another is would be laterite. So, and based on this thermodynamic simulation, we did 4 experiments. There are 3 kinds of the parameters for optimal condition. First one is CO dosage and CO2 flow rate and the temperature. The research revealed that arsenic removal efficiency increased with increase in CaO dosage and temperature. However, lower silty gas flow rate favors removal of arsenic. Finally, the maximum arsenic removal efficiency was 97.3%, and with 5 gram of CO dosage and 100 milliliter per minute surface flow rate and 60 degree of temperature. This is the SRD analysis result. SRD analysis was carried out to investigate the surface of each precipitation according to Ferguson and the pH. Within 2 minutes, the first picture, all crystals became calcite and laterite, but even though no calcium arsenic observed on the XRD analysis, arsenic concentration in solution kept changing with time. This means arsenic removal includes surface absorption and incorporation with the calcium carbonate crystal. This is the SEM and EDS analysis result. And the lower concentration of arsenic can be resulted like orthorhombic calcite, like a calcite, but high concentration of arsenic resulted in spherical calcite. So further study revealed the removal of arsenic includes combined effect of the surface absorption processes and incorporation of arsenic ions within calcium carbonate crystals. The last one is molecular dynamic simulation. Molecular energy potential maps showing most electronegative in range of the yellow and the red, and the most electropositive in the range of the green and the blue one. Yellow radicalisms in arsenic being electronegative can possibly affect outer positive atoms, such as divalent calcification. To provide this as option to further investigate the possibility of the calcium and arsenic interaction. And this picture is the calcium ions reacted the oxygen ions, not the arsenic ions directly. So actually all the things of the simulation, like thermodynamics or molecular dynamics, is just theoretically. Actually, the experimentally, all things not proven yet, but we have a lot of plan to prove this mechanism, and we have many plans to experiment. And the conclusion, calcium arsenide has a limitation, so integrated carbonation to overcome this limitation. And finally, removal efficiency about 97.3%. And the crystal share of calcite change according to concentration of arsenic. After around 2 minutes, all crystals become calcium carbonate. Arsenic removal includes surface absorption and incorporation with the calcium carbonate crystal. That's all. Thank you.
I think we probably discussed about arsenic 5 oxidation rate, right? So you know arsenic 3 is also a problem. Maybe in reduced oxidative state, arsenic 3 is formed, for example, in underground water. So do you think with this kind of experiment, with this kind of technology, you can also effectively remove arsenic 3?
Actually, among the thermodynamic simulations, the arsenic 3 is not related with the calcium ions, but the molecular simulation we find there's a possibility to remove the arsenic by a calcium ion, but actually the experimentally it have not improved yet, so we will do the experiment about arsenic 3 as well.
So just
Actually, experimentally, as you mentioned, the lower, the higher temperature, the higher efficiency of the removal arsenic. But actually, the mechanism or some improvement is not founded by myself. So it will be from the other analysis, like some particle or some STEM analysis more. So after then, I will, if I have chance, I will explain this. Thank you.
한국말 할게요. 여기 보면은 지금 CAO 도시지하고 템퍼처에 대해서 지금 요 에피션시가 차이 나는데 여기 CO2 플로레이트는 차이가 거의 없는 거잖아요. 그죠? 그러니까 뒷부분에 무슨 하이브 없었고 다이나믹 시뮬레이션 이런 저런 말씀하셨을 때 CO2 가스는 큰 의미가 없는 것 같아요. 지금 그러니까 저번 학기 때 제가 잠깐 말씀드렸던 것 같은데 이산화탄소가 지금 절감되는 효과와 그거 플러스 지금 아세닉 중금속이 제거되는 효과인데 지금 모든 설명이 다 뒷부분은 앞에 부분이 없는 것 같아요. 그러니까 CaCO3를 만든 이유를 모르겠어요. 네, 그 CaO하고 중금속하고의 반응이 더 크리티컬하지 않냐. 굳이 그걸 CaCO3를 왜 만들어야 되는지.
말씀드렸는데 사실 뭐 라임을 이용해서 칼슘 알세네이트를 침투시키는 게 좀 커먼한 증거제 기술이었는데 이게 지금 안정적이지 않다는 게 가장 제기되는 문제입니다. 이 기술에서. 그래서 칼슘 알세네이트를 만들어서 제거를 하는 건 좋지만 이게 만약에 지속되지 않는다고 하는데 그리고 실제로 그 상황은 폐수가 공기 중에 CO2가 있는데 만약에 CO2가 많고 CO2가 계속적으로 그 바깥으로 계속 바깥 그러니까 CO2가 있는 환경에 계속적으로 CO2가 방치된다고 그 폐수가 방치된다고 하면은 결국 다시 칼슘 카보네이트가 생성이 되게 되거든요. 그러니까 어차피 언젠가 생긴다고 하면은 엑셀러레이트 카보네이션을 통해서 한번 칼슘 카보네이트를 만들어보고 그 사이에도 혹시나 알세닉이 제거되는지를 먼저 본 거고 그리고 만약에 제거가 된다면 조금 더 좋은 가장 옵티멀한 컨디션이 뭔지를 찾기 위해서 이 실험을 진행한 거기 때문에 그러니까 뭐 CaCO3를 만든 이유는 아무래도 칼슘 알세네이트의 가장 한계점인 불안정성을 안정적으로 만들기 위해서 한 실험이고
그 다음 슬라이드 보면은
네.
그 다음 요거
네.
한카스님 제가 정확히 의도한 것 같은데 기소의 농도에 따라서 실험했나요 혹시? 아까 높은 농도일 때는 다른 메커니즘이 나오고 하는 것인 것 같은데 그 부분만 간략하게 한번 더 한국말로 이해가 안 돼서.
네. 먼저 이 전체 실험은 사실 총 15ppm의 알세닉 솔루션으로만 진행을 했습니다. 대체적으로 원래 산업 회수에서 알세닉의 농도는 다 다르지만 보통 10에서 20으로 논문적으로 잡고 있기 때문에 저희가 15mg으로 잡은 거고요. 그렇게 해서 진행해 주셨는데 조금 더 메커니즘적으로 이해를 하기 위해서 15mg/리터 알세닉이랑 500mg/리터 알세닉 용량 두 가지를 가지고 그 SMM으로부터 그 크리스털을 확인하기 위해서 추가적으로 실험을 한 내용이고요. 알세닉 안에 15 원래 칼사이트 원래 칼슘 카보네이트는 육방형계로 알려져 있는데 15mg/리터 알세닉에서 진행했던 카보네이트는 실제로 육방형계로 실제 칼사이트성 모양이 나오는데 하지만 조금 높은 500mg/리터 알세닉 용액에서는 그 칼사이트 모양이 이렇게 각진 게 아니라 조금 더 라운드 형식으로 나왔다는 얘기고요. 근데 이게 아마 핵 형성이라던가 어떤 칼슘 카보네이트 형성하는 데 있어서 알세닉이 조금의 방해한 게 있을 것이다 라는 가능성을 일단 보려고 이 분석을 진행한 것입니다.
높은 아세닉 농도일 때는 제거 효율이 더 낮나요?
그리고
그러니까 이걸 왜 했는지, 어떤 이유 때문에 높은 농도, 낮은 농도의 메커니즘이 다르다고 생각합니다.
일단은 논문 다른 기타 논문 기반으로 이 실험을 진행한 거였는데 알세닉의 유무에 따라서 변화가 있다는 것을 확인하기 위한 거였는데 높은 알세닉에서는 아무래도 낮은 알세닉 농도에서는 그다지 변화가 없어서 혹시나 이런 변화가 알세닉에 의해서 있는지를 보기 위해서 또 일부러 높은 알세닉을 본 거고 효율은 사실 저희가 이 실험을 진행하면서 따로 분석을 제거 효율에 대한 분석을 진행하지 않았습니다.
알겠습니다. 또
Good morning to you all. So my presentation today is about neutralization and recycling of high alkalinity liquid derived from alkali activation of CFVC flash by carbonation. The content of my presentation includes introduction, mathematical and method, result discussion, and conclusion. So about rare earth, we know that rare earth is used in many applications of our life, from domestic use and industrial use or for high technology use. And it is very rare to find the profitable rare earth mine. So that's why rare earth is categorized as the most group of critical material. And about coal ash. So coal is used to produce electricity in the power plant. And the byproduct of this process is coal ash. And so far, like around the world, a lot of coal ash or coal combustion byproduct is produced. And most of them is utilized, but some remain huge amount for us is not utilized. And one more problem with coal, like electricity derived coal combustion, is about carbon dioxide emission. So our research is to develop solution for both problem of coal ash combustion of coal ash production and carbon dioxide emission. About coal ash disposal. So coal ash disposal creates some environmental issues. For example, it's occupy large area of land to coal ash disposal. And in coal ash, it contains significant amount of heavy metal. If this heavy metal is in contact with water, and it can be leached out and contaminate the water body nearby. So, but one more positive aspect is we can use chloride as a raw material for like other application, like in the construction or recovery of valuable material. Then why we talk about chloride as a source for rare elements? Like during the long geological process, rare element can be introduced to the coal basin, and after the coal is burned, this concentration of a rare element in chloride is increased. So that's why they consider rare element chloride as the most promising source for rare element besides the rare ore. And to consider the chloride as a source of rare element, we have to look at the potential economic significance of chloride. It's defined by the total content of heavy rare elements and total content of critical rare elements in the sample. And also the total concentration of rare elements in chloride is very important. So to recover rare elements from coal ash, one method is widely used now is about alkali activation or alkali treatment, because for us, the rare element in chloride is trapped between the amorphous silica and alumina matrix, and the normal condition like acid leaching is not sufficient because it cannot break the amorphous matrix. That's why alkali material is utilized to break this matrix and release rare elements to be exposed to the chemical in the downstream process. And USA, like in Department of Energy in US, they invest a lot, like efforts and funds to develop for us as source for rare elements. And they also widely use alkaline activation to recover rare elements. And also there was developed process to recover rare elements by supercritical carbon dioxide extraction. So from our study, we are trying to combine both this process to provide environmental friendly method for recovery of rare element, utilize carbonation and alkaline activation. Also, the carbon mineralization technology is a very advanced process to be commercialized in the future, now and in the future, and also contribute to carbon dioxide sequestration. That's why this program of our lab, development roadmap, and our research in this area, we utilize carbon dioxide and alkaline material combined together to produce enriched red chloride, enriched red chloride, and also sequestration of carbon dioxide. And our aim is to develop the process that effectively enrich red, utilize carbon dioxide, and also but in combination with alkaline activation. So our sample is the CFBC class. CFBC stands for circulating fluidized gas combustion technology, and this technology can combust the wide range of fuel, because the conventional combustion technology can combust high range coal, but this technology can combust the low rank coal and with high efficiency. And the most important thing is the temperature of this technology is around 800 to 900. So it's reduce the nitrogen emit from the boiler. And because of high sulfur content in the coal, in low rank coal, that's why limestone is supplied to capture sulfur, to avoid sulfur removed from the boiler. And because this forests have high content of calcium, so it's also reduced the application of this forest as a material for construction or for reutilization. So this is our design, our team design for enriched red elements utilize multi-step carbon dioxide utilization, and it combined with alkali activation and chemical recycling. So first about sample characterization. So we can see that easily see the content of calcium is significant in this sample, and also with high content of silica and alumina. So it's also present in the mineral composition by the significant amount of phosphate and calcium-based compound like calcite anhydride or pollandite. And about the content of rare elements in the samples, like this, the rare element content in this sample is compared like a little bit similar to the average chorus of the world, but it's lower than enriched rare chorus in like US or in China, where they have high background of rare content. So regarding to the sample, the CFBC technology combust coal is in the range of temperature 800 to 900, while the PC boiler combust coal in the range temperature 1,300 to 1,600. So low temperature means less red element melts and less red element can be trapped in the amorphous phase. So that's why we have more opportunity to recover red element from CFPC flyer than it's more easy to extract red element from CFPC flyers than PC flyers. So when we go to alkali activation, so in PC samples, we found that with the increasing of condition like temperature, pH, or time, first, it would dissolve, it modifies the surface of the particle, and it's dissolved on the surface. But after that, when we increase the condition of temperature, pH, and time, is the dissolved portion will react with each other, and then it will precipitate on the surface of particle. Then it's like it limits the possible of red element exposed to the chemical environment. And this story is a little bit different with the CFBC flash, because in CFBC samples, we have high concentration of calcium. That's why calcium is first react with alkali material, and then this calcium again react with silica and alumina to reduce the effect of alkali activation. That's why we are trying to remove calcium portion by carbonation first before do alkali activation. And this is the mechanism proposed for alkali activation of high calcium system. So with the increase of calcium content and with increase of condition, so more calcium is involved in the like precipitation product, and calcium also with the increase of temperature and pH, calcium is replaced. Like first aluminum is react, and then calcium replace aluminum. Then aluminum is freeze to the environment, and calcium take place of aluminum in the like precipitation product. So we like our propose like alkali activation and can enrich rare elements, but is associated with high alkali liquid production. So we can use carbonation of this liquid can reduce like environmental issue. And also we can recycle this alkali material just by utilizing carbon dioxide through carbonation process. So there's a main achievement. So from CFPC class, first we do alkali activation. Alkali activation can, like after alkali activation, we do filtration. So the high alkalinity liquid, it has pH around 14. So by doing carbonation, by adding carbon dioxide, the pH is reduced by around 8.3. So this process is divided by 3 into 3 region. So first in the one region number 1 is about carbon dioxide dissolution, and after that in region number 2, the dissolved carbon dioxide, like the carbonate ion, is react with sodium and sodium silicate, and is produced like silica, amorphous silica, also sodium carbonate, and in the number 3 region, like more carbon dioxide is less. So by utilizing carbonation, we can neutralize this liquid, and the alkaline material is recycled again by adding a calcium oxide. So there's a byproduct of this process is almost calcium carbonate include calcite and laterite. It's recycled, and the pH is increased again to produce sodium hydroxide. And there's another byproduct of the alkali activation combined with carbonation is amorphous silica, also some sodium carbonate, like precipitate along with amorphous silica. So my conclusion is the carbonation demonstrates a sustainable process to promote eco-friendly enrichment reactant through alkali activation, and high alkalinity liquid will neutralize and recycle for the next cycle. The enrichment rate of red element is around 7.3%. So it's increased the content from 380 to 409. Also, 59.1 kilogram of carbon dioxide was sequestered per ton of fly ash. And other byproducts were recovered, like such as calcium carbonate and cyclotron, and also amorphous silica powder were recovered. Thank you very much.
시간 준비되었고 하나 두 개만 질문 있으시면.
Okay, so I have a question. In the introduction, you talked many about the potential to recover the rares, and what is the most different, the most advantages of the alkali activation to recover the rares compared with the current methods in the world at this time?
So I show you about alkali activation because it's required to it's used to enhance the possibility of well recovery. And our research, we include carbon dioxide utilization. It has some advantages. First, we can capture carbon dioxide. Second, because in this sample it has high content of calcium. This calcium is reduce the efficiency of alkali activation. So by utilizing carbon mineralization, we remove calcium. That's why we can increase the efficiency of alkali activation. And number 3 advantage is this carbonation process can recycle the alkali material. So it's reduce the process of the process.
Thank you.
안녕하세요. 한국지질자원연구원 탄소박물관 사업단 소속으로 연구하고 있는 한양대학교 정학연구과 석사과정 최혜영입니다. 제가 이번에 발표할 내용은 플라이애쉬의 탄산화를 통한 기수오염 폐수 처리에 관한 내용입니다. 발표는 다음과 같은 순서로 진행되고요. 연구 내용 발표에 앞서 이번 연구에서 다루고자 하는 이슈들에 대해서 소개드리도록 하겠습니다. 첫 번째는 이제 클라이밋 체인지 이슈입니다. 모두가 다 잘 아시다시피 기후변화 문제는 매우 심각하고 그중에서 이산화탄소가 가장 심각한 것으로 여겨지고 있습니다. 그림 보시면은 IPCC 기후변화 시나리오에 따르면 2050년 지금 같은 추세로 이산화탄소가 배출될 경우 4도에서 6도씨 정도로 기온이 상승할 것으로 예상을 하였습니다. 2015년도에 파리에서 열린 협정에서는 이런 기온 상승을 2050년까지 2도씨로 제한하는 것을 협정을 하였고, 이에 맞춰서 이산화탄소 배출 저감을 하기 위해서는 이제 대책이 필요한 시점입니다. 두 번째 이슈는 알칼리성 산업 폐기물입니다. 전 세계적으로 많은 양의 건설, 시멘트, 발전소와 같은 산업으로 배출되는 많은 양의 폐기물들이 환경적으로 처리하는 데 담대한 비용과 발전된 기술이 이제 필요합니다. 그러나 최근 이산화탄소 저장과 활용하려는 기술들에 집중을 하려면서 알칼리성 폐기물의 이산화탄소 감축 잠재력에 대한 연구들이 많이 보고가 되었습니다. 한 네이처 논문에 따르면 연간 20억 톤의 알칼리성 산업 폐기물이 발생이 되고, 이러한 폐기물들은 연간 200만 톤의 이산화탄소를 저장할 수 있는 잠재력이 있다고 밝혔습니다. 그렇기 때문에 알칼리성 고체 폐기물을 이용한 이산화탄소 방문화 같은 기술들은 2050 탄소 중립 목표 달성에 있어 전략적으로 활용될 수 있는 녹색 기술로 주목받고 있습니다. 네, 그리고 세 번째는 기후 오염에 대한 문제입니다. 앞서 이제 송영주 연구원님 발표에서 설명되었으니 간략하게 설명을 넘어가도록 하겠습니다. 비수는 아주 미량으로도 병변이나 피부병, 심혈관 질환 등 매우 심각한 질병의 원인이 되기 때문에 식용수의 경우는 10ppb 이하, 그리고 농업용수로는 100ppb 이하 정도로 제한이 되고 있습니다. 그렇기 때문에 수질 내 기후 오염에 대한 처리 문제가 있다는 것을 알 수 있습니다. 그래서 이런 세 가지 이슈를 종합하여서 제가 처리할 수 있는 방법에 대해서 생각을 해보게 되었습니다. 알칼리성 산업 폐기물인 플라이애쉬를 이용하여 중금속을 충전시켜 제거하였다는 연구들이 이제 결과들이 많이 있음을 확인하였고, 우리가 시도하려고 하는 플라이애쉬의 탄산화 방법을 통한 연구는 이제 여러 중금속을 다루긴 하였지만 비소물질을 다루지 않았거나 탄산화 과정이 없었기 때문에 이번 연구를 통해서 이전 결과들을 기반으로 이번 연구를 통해서 플라이애쉬 탄산화를 통해 기후 오염 폐수 처리가 가능할 것이라고 이제 예상을 하였습니다. 그렇기 때문에 광물학 기술이 주로 이제 적용되는 알칼리성 폐기물 중 하나인 플라이 애쉬를 이용하여 용액 내 비소 제거하는 실험을 진행하였습니다. 우선 실험에 앞서 저희 사업단 연구실에서 진행되었던 이전에 비소와 중금속에 관련된 연구들에 대해서 간단히 해봤습니다. 2009년에는 광미에 들어있는 아르세닉 비소와 중금속으로 인한 농출 문제에 대해서 다룬 내용이 있습니다. 폐광미가 빗물이나 지하수와 같은 지하수로 인해 농출되는 문제점을 다루었고 2013년도에는 이제 가속탄산화를 이용한 중금속 비소는 아니었지만 니켈, 줄이 이제 낙과 같은 중금속 안정화에 대한 연구가 있었습니다. 그리고 이제 현재 2017년도에는 산화칼슘을 이용한 비소 제거 연구가 시작되면서 비소 제거를 위한 탄산화법에 대한 연구가 본격적으로 시작이 되었고 현재는 앞서 발표된 비소 제거 연구와 같이 산화칼슘이랑 비소, 혼수물질 실험을 통해서 화학적이나 물리적인 어떤 메커니즘 규명에 관한 연구가 진행되고 있습니다. 이를 기반으로 실제 산업에 적용시킬 수 있는 활용에 대한 아이디어를 가지고서는 이번 연구를 진행하게 되었습니다. 공통적으로 적용이 되는 알칼리성 폐기물의 탄산화 사이클은 다음과 같습니다. 물질로 보시면은 산화칼슘 그리고 수산화칼슘, 탄산칼슘 이 세 가지 물질이 수화, 탄산화, 화소 과정을 통해서 이제 만들어지게 되는데 그리고 최종 산물은 탄산칼슘이고 이산화탄소와 반응을 한 후 제지나 시멘트 그리고 여러 산업들에 이용이 되고 있습니다. 이외에는 제올라이트 합성이나 알칼리성의 성질을 이용한 토양 개질에 이용이 되고 있고 이번 연구에서는 수질 내 비소를 제거하는 어떤 침전제나 혹은 흡착제로서의 물질로 활용하게 되었습니다. 네, 그래서 이번 연구의 목적은 석탄 비산제를 이용한 수용액 비소 물질 안정화 가능성을 확인하고 가속 탄산화 방법을 이용하여 이산화탄소를 활용한 비소 제거 기술 개발을 목적으로 하였습니다. 실험 방법과 재료에 대해 설명되어 있습니다. 우선 실험 방법으로는 15ppm의 비소 용액 500ml를 국별 준비했던 뒤 플라이 애쉬를 주입하여 소화 과정을 거치게 됩니다. 네, 그러면 용액은 12 정도의 높은 pH를 나타내게 되고 비소는 이제 비산제 안에 이제 칼슘이나 어떠한 흡착 가능한 성분들이랑 반응을 하게 됩니다. 네, 이후 이산화탄소를 주입 후 산화칼슘 및 탄산화 반응을 통해 산산칼슘으로 전환이 되고 pH가 12에서 6이나 6.5 정도로 어느 정도 안정화되게 됩니다. 6에서 6.5로 안정화된 상태가 되면은 필터로 교체를 분리하여 분석을 위한 샘플을 하는 실험을 하고 있습니다. 주로 솔리드나 엑사이드나 티지를 이용해서 결정상이나 이산화탄소 고용량을 확인하게 되고 그리고 이제 액체 샘플은 ICP나 비소 피트 분석을 통해서 이온 형태의 성분 물질을 확인할 수 있습니다. 그리고 제가 이번 실험에서 사용한 플라이시 샘플에 대해서 설명드리겠습니다. 우선 저희가 가지고 있는 샘플 중에서 이 샘플로 제가 실험을 한 이유는 탄산화 과정으로 반응하는 물질인 산화칼슘이 많은 것을 이제 선택을 하게 되었습니다. 주로 산화칼슘은 발전소에서 황 성분의 제거를 위해 생성체를 투입하게 되는데 이는 이제 발전소마다 투입하는 양이 다르고 이제 발전소의 그 샘플을 가져오는 시기마다도 다르기 때문에 노멀라이징이 매우 힘들고 거의 불가능하다고 볼 수 있습니다. 그래서 산화칼슘의 양과 이외에 일반적으로 중금속 흡착 능력이 있다고 알려져 있는 실리카나 철, 황암과 같은 이제 물질들을 고려해서 그 반응을 해볼 수 있습니다. 앞서 XRF 결과와 같이 정량 분석을 통해서도 비소를 제거할 수 있는 성분들에 대해서 이제 확인할 수 있습니다. 비정제 물질은 주로 알루미늄이나 철과 같은 물질들이 될 수 있고 이외에 헤마타이트 그리고 칼슘 성분 물질들을 확인했습니다. 이 샘플의 분석 결과를 기반으로 실험을 진행했습니다. 그 다음은 실험 결과입니다. 플라이 애쉬 투입량에 따른 제거 효율과 투기 비소 농도에 따른 실험을 진행을 하였습니다. 비소 농도는 수질 오염 측정용으로 사용되는 분석 키트를 사용을 하였습니다. 고정 변수로는 이산화탄소 주입량과 도관 속도가 있는데 이는 이제 저희 연구실에서 진행된 송원규 연구님이 실험에서 얻은 데이터를 기반으로 고정 변수를 설정하게 되었고, 그 결과는 플라이시의 투입량이 많을수록 그리고 비소의 초기 농도는 낮을수록 효율이 높아지는 경향을 보였습니다. 그러나 이제 실험 결과가 충분하지 않아 최적화 변수를 찾기에는 많이 부족하고 하지만 최소 70%에서 최대 97.8%의 효율을 보았을 때 비소 제거 물질로 활용하기 위해 이제 더 연구를 진행할 수 있겠다고 이제 판단을 하였습니다. 이제 현재까지 진행된 연구에서의 한계점에 대해서 제가 생각한 바를 말씀드리겠습니다. 이제 바로 첫 번째는 플라이 애쉬 안에도 중금속의 교동에 대한 확인이 없다는 점입니다. 주로 석탄 비산제와 알칼리성 폐기물에는 중금속들이 함유되어 있는 것으로 알려져 있는데 이런 물질들이 탄산화 과정으로 인해서 중금속 검출이 될 수 있고 이런 것들의 문제점이 생길 수 있는데 그런 점을 확인하지 못한 것이 일단 첫 번째 문제입니다. 그리고 두 번째는 이산화탄소 활용 기술로서의 접근이 부족했습니다. 플라이애쉬를 비소 제거 물질로 활용을 하였지만 이산화탄소 활용 기술로서 이산화탄소가 얼마나 활용이 되고 환경적으로 전체적으로 어떤 영향을 미칠지 확인해야 하는데 이는 이런 흡착 제거 기술뿐만이 아니고 이산화탄소를 활용한 기술이라면 모두 거쳐야 하는 분석 과정입니다. 애쉬의 분석을 통해 이제 전 과정에서 이산화탄소나 환경적으로 어떤 영향을 미칠지 평가를 해야 합니다. 저의 결론을 말씀드리겠습니다. 첫 번째는 석탄 비산제 탄산화 과정을 적용한 결과 이제 비소가 제거가 가능한 것으로 확인되었습니다. 이제 현재 실험 결과에 따르면 최대 제거 효율이 97.8%로 높게 나타났습니다. 그 다음은 앞서 얘기했던 한계점들을 이제 극복하기 위한 다음 연구의 필요성입니다. 중금속 검출과 플라이애쉬의 이산화탄소 활용과 관련한 다음 연구가 진행되어야 하고 그래서 이제 이 연구의 최종 목표는 비소 오염 폐수를 처리할 수 있고 이산화탄소를 활용하는 기술을 개발하는 것인데 이번 발표는 이러한 연구 과정에 대해서 전하겠습니다. 이제 다음은 제가 이제 활용한 레퍼런스들이고 혹시 질문이나 연구에 대한 도움도 주시면 감사하겠습니다. 감사합니다.
네, 질문 있으시면 해주시면.
그게 커뮤니케이션을 통해서 조금씩 올라오는 것을 확인을 못했어요. 그러면 커뮤니케이션을 인해서 다른 소비자들이 적어지지 못하고 그거에 대한 다른 처리가 되는
이제 주로 플라이애쉬 안에는 중금속들이 함유되어 있다고 많이 알려져 있는데 이거는 이제 저희가 탄산화 과정을 보면은 pH가 12에서 6 정도로 떨어지게 되면은 중금속들이 노출될 수 있는 환경이라고 이제 생각할 수 있습니다. 그런데 이제 많은 이전 연구들에 따르면 탄산화를 통해서 많은 중금속들을 이제 안정화시킬 수 있다는 연구들이 이제 많이 언급이 되어 있는데 이제 제가 이번 실험을 통해서 그 점을 실험적인 데이터나 그런 부분을 확인하지 못했기 때문에 혹시 기회가 된다면 다음에는 그 부분을 이제 다뤄서 연구를 진행해 보도록 하겠습니다.
하나만 질문 그러니까 탄산화를 통해서 지금 비소가 플라이애쉬라는 물질과 그 물질의 탄산화 반응을 통해서 그 안에 있는 비소를 제거할 수 있다는 식의 지금 흐름인 것 같은데 맞나요? 제가 이해한 게.
이제 플라이애쉬 안에 있는 비소가 문제가 될 수도 있지만 우선 이번 실험에서는 수용인데 이제 비소 오염 지역이 이제 폐수 처리를 위한
그러니까 바깥 영역에 있는 비소라든지 아니 다른 뭐 비소가 아닌 어떤 다른 중금속들은 흡착할 수 있는 힘이 없는 건지 왜 굳이 비소를 통해서 했는지 거기에 대한 언급을 좀 해주세요.
주로 이제 이런 알칼리성 흡착 플라이애쉬는 다른 중금속들도 흡착할 수 있다는 것으로 이제 언급이 되는데 제가 이제 비소 물질로 식으로 다루게 된 거는 제가 기존에 연구 논문들을 살펴보았을 때 주로 이런 논문들이 많이 나와 있었는데 크롬이나 뭐 다른 중금속 물질들이 있었지만 기소 물질을 다룬 논문은 없었기도 하고 그리고 탄산화 과정이라는 이제 또 그냥 단순히 플라이시를 흡착제로만 사용한 게 아닌 카보네이션을 이제 같이 이제 적용을 해왔기 때문에 그걸 같이 기소에 적용한 연구는 없었기 때문에 기소를 선택하고
네, 알겠습니다. 네, 수고하셨습니다.
감사합니다.
I will present this title today. And this is a very basic experiment or a very basic study. So we will go through it. So the main point is to recover nutrients like nitrogen, phosphorus, and potassium from human urine by using the alkaline stabilization and carbonation. So the contents that are involved in this experiment are introduction of mercury, relevant discussion, and conclusion. So as an introduction, the human urine is a very good source for the nutrients because it has a potential, it has nutrients like the nitrogen, which is the main component of the urine, the phosphorus, and also the potassium. And there are a lot of studies or a lot of mechanisms that we can use to recover these nutrients from the human urine. Among this is one of the best and one of the solution is to use alkaline stabilization method. So this method will enhance the value of the solution, higher pH, which will enhance the loss of urea, which is the main and the most important component of the urine, and it will stabilize the urine from the lost urea. So this stabilization method has many advantages. The first one is it works very effectively. We can use it as a fertilizer as a result. And also we can kill bacteria from the urine. And also we can produce other types of fertilizer other than nitrogen. However, by using this calcium hydroxide or calcium oxide stabilization method, we can have excessive calcium as a result, which can disturb the nutrient distribution plants. And also, if we are using advanced technologies like the reverse osmosis method, then we can produce cells or the equipment might be destroyed. So we have to be careful with how much calcium we are using. So in the urine chemistry, so the main component, as I have told you earlier, is the urea, and we have to keep that one. And use time, we can use this urea because of different enzymes in the urine or in our toilets. So and then there is a half-life of urea. The half-life of urea, it might take around 40 years to get this urea at a room temperature. So we have to optimize some of the functions like temperature and the filter most important things in recovery of this component. So we have used the waste shell and we have tried to get municipal solid waste for sustainable results. So this is the classification, and we know that the global manufacturing waste is increasing. And then one of the manufacturing waste is calcium, and this calcium is a good source for calcium carbonate. It can be used in universal applications. So we can also see that by using this waste material, we can manage our manufacturing waste in a sustainable way, and we can see the sustainable whole well. So the objective of this study is first to synthesize calcium hydroxide from the waste shell and then we can recover the NPK, the nitrogen, phosphorus, and the potassium by using this synthesized calcium oxide, and also finally to remove the calcium hydroxide we have used earlier. So the hypothesis is we can get a good result or a good recovery of this the NPK, and also we can inactivate the pathogens. High grade of fertilizer can be obtained. So these are some of the hypotheses. So in the material methods, first the synthesis of calcium hydroxide is used by the Soldier method, and then we follow this experimental rule and we finally get the calcium hydroxide. And then for the stabilization of the urine process, we have used different concentration of calcium oxide from 0.1 to 1 mole of calcium oxide, and we autoclave it, and then we filter it, and finally we carbonate the filtrate to remove the excessive calcium, and then finally we measure the NPK and as well as the others. So for the resulting expression, we have characterized the moisture before we use, which is mainly calcium carbonate, and it is the calcium oxide content is very high, and the XR also shows that one between the carbon in the oxygen form. Activity test TJ, all this indicated that there is calcium carbonate, and for the synthesized calcium hydroxide, we have obtained putlandite both in TJ and XRD is still as well. So for the recovery of nutrients and for the stabilization process, so we get a good recovery of these nutrients at 0.1 mole of calcium oxide, and as the content of calcium oxide increases, which is up to 1 mole, it decreases. This is because of the urea. It degrades at a very alkaline solution. So it has an optimum pH between 10 to around 12. So in that pH, the hydrolysis process or the loss of the urea will be inhibited. However, if we raise the pH above 12, then it can degrade the urea again. So we have to be careful with the pH, and then that's why at 1 mole, the pH is around 13.5, so that's why the recovery is decreasing. And we have get an optimum condition at 0.1. However, in the phosphorus case, we know that phosphorus reacts with calcium very well, so the phosphorus was decreased from 14.5 without the calcium to 0.55. So this was the results that we have obtained, and also we have also studied the temperature, so temperature at 50 and 60. So this two results were taken from previous other studies, as we have to take the other temperatures also, but at pH 60 and 60, the recovery of the nitrogen was here. And for the effect of the time, we also studied the time. So at around 5 minutes, within 5 minutes, we get, after 5 minutes, it becomes constant. So we recover around 700 milligram per liter of nitrogen. And as I told you earlier, the TP was after 5 minutes, it's a 0. So for the inactivation of the pathogens, both the bacteria and E. coli were inhibited by the calcium receptor. And for the carbonation process, so we have said that pH is the most important thing, but when we are using carbonation, we know that the pH decreases, right? So if the pH decreases, then we might think that we will lose the urea again. So that's why we have to the urea by carbonation. So, but there is a loss, but the loss was not that much significant. So we can compromise this situation, and we can continue the carbonation process to remove the excess calcium that we have used earlier. So as a conclusion, this should contribute as a good source for the calcium and supplement material. And this calcium oxide showed a significant stabilization and recovery of nutrients. And both temperature and residual calcium oxide have shown a good result also. And finally, future studies have been have been suggested to check